Now, we come to the feeds, that is now we are talking about the various feed types. First of all, what are the major considerations for selecting a particular feed? What do we mean by over here right now? Whether it should be a coaxial type, whether it is a microstrip type, could be slot line type feed, or could be a corresponding planar line like coplanar lines. Since the antenna is a planar, the feed in general will be a planar type feed, planar line, but in addition we have a coaxial line feed which is a not a planar one, but it has some of the advantages. That is why in some of the cases we use coaxial line as a feed. But before which what is the function of the feed? That basically it provides efficient transfer of power between the source and the antenna. We know that the antenna impedance, basically the input impedance of the antenna should match with the source impedance, which is for all RF sources, microwave sources 50 ohm. And naturally, since the antenna is looking into free space, which is 377 ohms. So, basically your antenna is acting as a impedance transducer between this 50 ohm and the 377 ohm. So, that sort of impedance transformation is there, and accordingly the feed point has to be chosen, so that at the feed point the input impedance is 50 ohm, okay, which will give rise to the efficient transfer of power. It should minimize spurious radiation from the feed. We just saw in the one of the slides that some of the feed types may give rise to spurious radiation, and which may corrupt the radiation pattern, and this spurious radiation should be kept to a minimum. And if one can isolate the two, the radiation from the antenna and the radiation from the feed, that is even much better. And most of the corruption takes place in the polarization of the radiation, not in terms of power. If you want a radiation from the antenna of a particular polarization, say linear polarization or circular polarization, the radiation from the feed may not have that type of polarization. So, it may affect the polarization characteristics to a large extent. And anyway, we know that if there is a radiation from the feed, that is a loss of power, because naturally that is not going into the desired radiation pattern. So, it has to be minimized. And the suitability of feed for the array application. When we are using this particular feed type, whether it is really suitable for the array feed structure or not, that is another major consideration, because some of these feed types, when they go about in this fashion, that fashion, they are going to generate a different cross polarization. Feed may generate a cross polarization and may affect it. Okay. This is the first feed type, coaxial line. Here it shows that this is a rectangular patch, top view is there, and from the back side, just like here you can see from the 3-dimensional view, this is a top metallization of the patch, this is the substrate, and the coaxial connector is going through this one. The center conductor goes from here, from the coaxial connector, goes through the substrate and meets the top metallization. It makes the metal contact. Okay. So, this is one over here, and this is the rest of the coaxial connector, that it feeds from the back side. Now, how to select the feed point, and depending upon the which mode you want to excite. So, for example, here in this case it is shown that this is the rectangular patch, and in the rectangular patch the field distribution, this is the half length here, the along the length of the patch, these dimensions are about lambda by 2, this is called the length of the patch, and this is the width of the patch, and this length should be around lambda by 2 for the frequency at which you want to radiate. And along the length of the patch, the electric field distribution will be this type. Do you understand why this electric field distribution will be like this? let me just give you the side view along the length, and this is nearly equal to lambda by 2, and this is the ground plane. So, as shown over here, along this edge, the electric field distribution, let us say this is maximum over here, again maximum on the opposite side, and it will be 0 in between, because it is a halfway variation. Halfway variation could have been something like this, 0 over 0 over here, and in between maximum, or it could be like this. But what we have over here is a field distribution along the edge, which is like this, that is maximum at this edge, 0 in the middle, and again maximum opposite in the at the other edge along the length. So, we have the electric field distribution and then there will be this fringing field. So, along the length of the antenna, the electric field distribution is maximum over here, goes through 0, and minimum again maximum opposite, that is what we call halfway variation. And here it is maximum because this is an open end of the antenna. There is a patch metallization edge over here, and here there is a free space. So, this is called an open end, not a short circuit over here. So, because of the open end, electric field has to be maximum. So, that is why the two ends are like this, and this mode is called TM10 mode. That is the dominant mode in a microstrip, rectangular microstrip patch antenna is TM10. Although it is a resonator type antenna, we are putting only two subscripts over here, not 3 subscripts, 10. 10, just like you say in the rectangular waveguide, the dominant mode of propagation is TE10, and the third subscript is not there. That is a transmission line waveguide. The third index does not have to be there, but in a resonator there should be a third index also, but it is not there because along the third dimension there is no variation. That is along the thickness. You have seen the earlier configuration, that is along this thickness h, substrate thickness. Since this thickness h is much less than wavelength, normally it is very small. We talked about 5 mil, 10 mil, maybe 1/16 inch, that is the order of substrate thickness we use. So, since this is much less than wavelength, there will not be any field variation, like we have drawn almost constant line. But along the other two dimension, there is a field variation. There is a 1/2 variation along the length, and along the other dimension, this dimension, this is width, there is no field variation. See, it is shown over here. If you look at this one, this is constant, field is constant along this and these edges, and halfway variation along this one. So, this 1 corresponds to halfway variation, 0 corresponds to no variation along the width. And third dimension, we are not for third dimension we are not putting any subscript, because the substrate thickness is very small. So, that is why these planar antennas, their characteristics are determined by the dimensions in the two plane, in the two directions, in a plane only, and the third dimension, that is along the thickness, that does not count over here. All the characteristics are independent of it, the reason being that the thickness of the substrate is much less than wavelength. Okay. So, in order to excite, one can excite 10 mode, one can excite 01 mode also, that is halfway variation along this and no variation along this, as shown over here, that along this edge there is no variation, it is constant, along this edge there is a halfway variation similar to that one. So, that is why now the index becomes this 0 corresponds to this direction, no variation, 1 corresponds to half a variation along this direction. So, one can excite either TM10 mode or one can excite TM01 mode, and the two modes will have a different resonant frequency. For 10 mode, the resonant frequency will be determined by this dimension of the patch, where there is half variation. For 01 mode, it will be determined by this dimension. So, naturally, the resonant frequency corresponding to this mode will be higher, because length is dimension is corresponding dimension is smaller. Okay. Something like lambda will be equal to twice w. If this is the width of the line, then corresponding lambda will be twice of w, and lambda corresponding to this will be twice of the length. Okay. Resonant wavelength. Now, how to select a particular mode over here using the feed point? Say for example, here in this case, let us come back to TM10 mode. If you want to excite this mode, at the feed point the impedance should be 50 ohm. Okay. And wherever the electric field is 0, the impedance is going to be 0, and wherever the electric field is maximum, that is at this point, at this edge, the impedance, input impedance is going to be high. So much so that for typical dimensions of the substrate etc., you use, the impedance at these edges could be something like 400 ohms, whereas it is 0. So, the impedance varies from 0 here to 400 here and 400 here. In between, it is going to be somewhere 50 ohm. Okay. So, one has to find out a feed point over this edge somewhere between here and here, and then one can find out relatively analytically easily if one knows what is the maximum impedance value over here at the edge. That one has to find out analytically. Only thing is, now the feed point will be located somewhere between this point, center, and here, and you can, if you put the feed point like this, somewhere like this here over here, then you will be able to excite that particular mode, and maximum transfer of power will take place from your source to the antenna. Similarly, if you want to excite this particular mode, the feed point should be along this edge, and again same consideration apply. Here along this line, the impedance is going to be 0, along this edge it is going to be maximum, and somewhere in between it will be 50 ohm. So, for TM10 mode, feed point could be somewhere here. For TM01 mode, it could be somewhere on this line. Is that okay? And basically the impedance variation from one edge to the center, it is of the type cos square function. Okay. When we talk about mode, I think we will have to go back to the your undergraduate rectangular, let us say go to the rectangular waveguide. In a rectangular waveguide, the dominant mode is TE10, okay, transverse electric, and the mode, basically when we say mode, it means the field distribution, the various components of electric field and the magnetic field, how they are varying along the cross section of the waveguide. And when we say TE10 mode, it means the field is have halfway variation along one direction, no variation, or it is constant along the other direction. Same thing we talked about over here when we were talking about TM10 mode, TE01 mode, TM01 mode. So, modes here are basically of transverse magnetic type, whereas in the rectangular waveguide they are transverse electric type. In a coaxial line, it is which type of mode? TEM, transverse electromagnetic mode. And in a microstrip line also, the dominant mode is very near to the TEM mode, not exactly TEM. Okay. Is that okay? And this here now it talks about the same mechanism we have been talking about. That is a rectangular patch shown over here, fringing field at these two edges. This is the feed line, and here it is the again the same field distribution which we have plotted over here, shown along one edge, with the fringing field etc. The separation is near lambda by 2, and this now if we resolve this fringing field, there will be one component over here and one component over here. Similarly, if you resolve this one, okay. Now, from the field distribution here and here, you can almost explain very easily what will be the polarization of the radiated field. That is, these two edges which are mainly responsible for radiation. These edges do not contribute to radiation because the field distribution is like this. So, whatever the radiation from here, whatever the radiation from field radiated from here, they will cancel out. So, this edge and this edge do not contribute to radiation, whereas this edge where that is what has been shown over here. You can see these two edges. It is not worried about these two edges because individually they do not contribute to radiation because of the halfway variation of the field. And here there is no variation, it is constant, and if you resolve this field into these components, the radiation from this component and this component, they will cancel out each other because they are oppositely directed and separated by lambda by 2. Okay. But these two are in the same direction, these components. So, they decide the polarization of the radiated field. So, in this case, the polarization of the radiated field is linear horizontal. Okay. Similarly, if you would have excited the mode along this one, TM01 mode, the corresponding polarization would have been like this. So, for TM10 mode, this will be the polarization of the radiated field. For TM01 mode, the polarization will be like this. Now, you can understand, is it? Okay. Naturally, the feed point will be different.
If I feed the patch antenna from the length side.
Which side? This one?
Yes.
Yeah. If you are feeding it from this side, see what we have seen that if you want to excite this mode, you have to feed somewhere here on this line. Okay. But if you want to excite the mode along this one, just wait. Okay. Yeah. You have to feed along one of these lines, because here at this bisector line the impedance is going to be 0. Here for this particular mode the impedance is going to be maximum over here. In between it is going to vary. So, you have to feed along somewhere line like this.
So, if I am feeding along the length side, which two edges will be responsible for the radiation?
Oh, which two sides will be? Okay. If you are feeding, let us say somewhere here, okay. So, there will be halfway variation along this, and this will be the field will be constant over here along this edge, and these two edges will be responsible for radiation.
So, it will be TM01 mode.
TM01 mode, yeah. So, for one mode, TM10 mode, these two edges are responsible for radiation. For TM01 mode, these two edges are responsible for radiation. Okay. And the larger the radiating edge, smaller will be the radiation impedance, and bandwidth will be more. Smaller the radiation impedance, that is larger the radiating edge, the bandwidth is going to be more. Okay. So, we have talked about polarization of the radiated field and linear along the resonating dimension. Okay. So, it is linear, and whatever they say for the TM10 mode, this was the resonating dimension and it was linear like this. For TM01 mode, this was the resonating dimension and it is linear along this. Okay. You can remember like this. before I go to this one, let me tell you what are the advantages of this coaxial feed. One of the advantages of this coaxial feed is that your antenna is on this side. You can say that there is a dividing line between the antenna and the feed part. The ground plane is coming in between. This is the antenna, this is ground plane, and this is feed. So, any radiation from the feed due to various types of junction etc., that will remain on the this side of the ground plane. So, that it will not go towards the antenna side. So, it really isolates, that is one big advantage, that it isolates the radiation from your antenna and radiation from the feed. So, that way it is one of the very good points for this one. Secondly, is that you can feed it at any point inside the patch metallization, which is not so easy with the microstrip type feed or the printed line feed. Okay. Now, in the microstrip feeds, the convenience with this type of printed line feed is that you have antenna, you have rest of the RF circuitry, and if you put everything together, it is better to have the feed line also on the same side of the substrate. So, it takes care of, you do not have to introduce unnecessary junctions. You can print the whole circuit, the antenna and the RF circuitry in the one go, and you do not have to put some sort of say in the waveguide we have in between those flanges etc. You do not need on any of those things, and that improves the reliability and performance of your whole system.
Like SOPs, active antennas are coming.
Yeah, that is right. System on chip. Okay, here this let us say rectangular patch, one can have a feed line like this, provided you get a 50 ohm point. Okay. Similarly, you can have the microstrip feed underneath the patch metallization, because here the limitation is you are feeding at the edge, okay, and at the edge the input impedance is going to be very high, likely to be, unless you have worked out the substrate parameters so that it comes out to be 50 ohm, otherwise it is most of the time it is going to be more than that, and you cannot really feed it over here. But if you want to feed it inside for 50 ohm, you can take the microstrip feed to a lower level. That is, you use two substrates, one and second substrate, and in between the first and second substrate you have a microstrip. That here will be the ground plane, then there will be a microstrip feed line, and then on the top you have the patch metallization. This is called proximity coupled feed. It is not a direct. See, this one is called butt feed on the radiating or non radiating edge of the pitch, and this is called the proximity coupled, that is the power from the feed to the patch antenna do not couple directly, but through the electromagnetic field coupling, and you can end it anywhere. This microstrip feed, this edge of the feed should be located where the input impedance is something like 50 ohm. So, you can take your microstrip feed inside in order to match with the generator impedance. So, that is proximity coupled feed. Then there is again which is called gap coupled feed. Here we have put a gap over here, some sort of a discontinuity, that the microstrip feed line ends over here, and between this and the patch there is a gap which we call coupling gap, because the input impedance over here is likely to be very high and it will not match with your feed line impedance. Okay. So, introduce a coupling gap over here, so the RF energy get transferred from here to here. You do not have to worry about what is the impedance at the feed point or what is the impedance of your feed line. But only thing is that depending upon the gap size, you may lose some power. So, normally you try to have this gap as small as possible, as narrow as possible. In that case, the corresponding RF capacitance will be high, and the more power transfer will take place from here to here. Okay. People have gone to the extent that in order to increase the gap capacitance over here, one can increase the width of the feed line, even going up to the whole patch. See, if you have the rectangular patch like this, you are feeding it, gap feeding you are doing, and maybe you can go as close as possible and come up to, let us say, this point. The only limitation is what is the minimum gap size you can fabricate, this one, because smaller the gap size, larger will be the RF capacitance, the electric field is going to be like this, okay. Gap capacitance will be more, and if you want to still increase the gap capacitance, you can increase the dimension here, even going to this extent. So, this will give extra gap capacitance, and it will reduce the insertion loss of the antenna. Okay. Fringing part, in fact, in this case the fringing will get reduced. So, it is mainly this edge which will be contributing to the radiation, because you have introduced this gap over here, fringing will get reduced over here. Okay.
So how can we decide the gap between the feed line and the patch?
The main thing is that the insertion loss depends upon the impedance between this and this, and the impedance is given by 1 over j omega c, capacitive reactance. Larger the capacitive reactance, smaller will be the impedance and smaller will be the insertion loss. So, try to maximize this capacitance, and this capacitance basically it is some sort of a parallel plate capacitance. It depends upon this dimension and the area, epsilon A by D. Okay. So, you want to maximize this area, that is, this is something like your comparable to your D, you want to reduce D, and this is your other dimension. Okay. So, this is the rule of thumb. Another way is that if you want to enter the feed point somewhere inside using the microstrip feed, because sometimes you do not have the choice, you have to use this feed, you can't go for coaxial feed. So, then you cut a sort of a slot, see here in this edge a slot has been cut over here, and microstrip feed goes right into inside, and this is the feed point where the input impedance is 50 ohm. This is one of the very common microstrip feed, which we call it as inset feed. Now, this is another feed type which looks somewhat rather complicated, but it has lots of advantages. That is why it is called best type of microstrip feed. Here is your in fact, here you can see there is one substrate here, one substrate here, and in between there is a ground plane. Okay. The dimension of the patch is determined by, because this substrate and this ground plane is just like your normal patch antenna, except that in this ground plane we have cut a slot over here, right underneath this one, the center of the patch. There is a rectangular slot over here, and this rectangular slot is being fed by a microstrip line on this side. See, here there is this substrate, this side there is a metallization, microstrip feed line is running over here, and the ground plane for this microstrip line is this one. Okay. And since it is you want to feed this slot, this microstrip should run perpendicular to this slot. So, when you feed power over here, this power gets coupled through this slot and then finally to the patch antenna. The advantages with this type of feed is that here you have feed portion which is on one side of the ground plane, antenna is on the other side of the ground plane. So, any radiation from the feed gets isolated from the radiation from the patch antenna. So, the radiation from the feed does not corrupt your radiation pattern. Okay. Second is that because this one, now you are using two substrates, one is this substrate, one this substrate. One substrate parameters you can optimize it so that the radiation is maximum. You can use this substrate which is low dielectric constant and large thickness to maximize the performance, the radiation efficiency and bandwidth. But this substrate which is for the feed part, you can choose the substrate parameter which is suitable for the circuit application and minimize the radiation from the feed part. So, this substrate you can use which is high dielectric constant and low thickness, small thickness. So, independently you can optimize these two. Here it is like this, that your slot is right at the middle of the patch, it is not offset from the patch.
Always middle, sir?
Middle. The reason is we have looked at the field distribution, let us say for 1-0 mode, if we go back, yeah. This was the electric field distribution for the desired mode. Electric field is maximum here, 0 here, again maximum over here. But the magnetic field distribution will be just the opposite. It will be 0 over here, maximum here and 0 over here. And in this case, the coupling between the slot and the patch is a magnetic field coupling. Okay. Yeah, here in this case, the magnetic field is going to be 0 over at this edge, 0 over here, and in the center it is going to be maximum. And the coupling between this patch and the slot is a magnetic field coupling, and we want to maximize this coupling for maximum transfer of power. That is why the slot is centered with respect to the patch. And rest, so far as the 50 ohm part is concerned, that the input impedance should be 50 ohm, because your feed impedance is 50 ohm. That is taken care of by the design of this particle part, because the impedance will get modified or transformed from your patch impedance to the 50 ohm through this coupling mechanism. Okay. So, there is in this feed, there is a transformation of impedance from the 377 ohm to the 50 ohm at this particular point, right. Then these are other types of feeds are there, mainly about the coplanar lines. As I said that in for some of these let us say RF amplifier or RF oscillator which are using MESFET devices, the geometry of the MESFET and the geometry 3 terminal geometry of this your CPW lines, they are compatible. So, because of this compatibility, one sometimes has to use these type of feed lines. Okay. Otherwise, one has to go through transition which unnecessarily reduces the efficiency of the antenna, and there will be increased insertion loss. Okay. Yeah, this is the comparison between the various types of feeds. It talks about coaxial probe feed, radiating edge coupled, non-radiating edge coupled, gap coupled, inset feed, proximity coupled, aperture coupled, CPW feed. If you go back, these are the coplanar waveguide feeds. This is aperture coupled microstrip feed. These are gap coupled and inset feeds, and this is butt proximity coupled feed, etc. So, these are the various feed types we have looked into, and this is coaxial probe feed. Now, we are comparing their characteristics. To start with, the various characteristics we are looking into, one is the spurious feed radiation, polarization purity, ease of fabrication, reliability, impedance matching, bandwidth achieved with impedance matching. These are the characteristics we are looking into, and on the basis of these characteristics we see how do they perform. In the coaxial probe feed, the radiation, spurious radiation is more because of the junction involved over there. Okay. But as such, it may not affect the radiation pattern, polarization of the radiation pattern, because it is on the other side. Okay. Whereas, the spurious feed radiation from the radiating edge coupled, this is a coplanar feed, because feed is in the same plane. This is a non-planar feed, coaxial line feed is a non-planar feed, because feed is not planar with the rest of the geometry. So, this is a coplanar, it is in the same plane. Spurious feed radiation is less if you are just talking about the feed part of it, because there is only one junction, and it is this junction, this junction which gives rise to some spurious radiation, not otherwise. So, spurious radiation is less here also, non radiating edge coupled, it is coplanar feed, radiation is less, but gap coupled, the radiation is the spurious radiation is more, because there is going to be radiation from this gap also, which we call it as a undesired radiation. Any discontinuity in the metallization is called a you can say impedance discontinuity, and it is going to give rise to some radiation. Okay. Then we have inset feed, again the radiation is going to be more, because it disturbs the metallization pattern. This is the inset microstrip feed. So, because the metallization pattern goes through these right angle bands, etc., and these right angle bands are going to radiate extra power. Proximity coupled feed, this is again the reason for the radiation in this case is, this is the proximity feed. Here the microstrip feed ends, there is an open end over here where it stops, microstrip stops, and the open end is always gives rise to the maximum radiation. From right angle band and other discontinuity, the radiation is going to be less, but open end is the main source of radiation everywhere. Even in the microstrip patch antenna, it is the open ends which radiate the maximum power. Okay. Aperture coupled feed, again there is an open end over here, but fortunately this is on the other side of the ground plane and will not add to your radiation pattern. CPW feed, here the radiation is less. The reason is, in the case of CPW, CPW is a balanced line. See, if we look at the let us just this is a coplanar waveguide. The coplanar waveguide is a planar version of your coaxial line. So, this metallization acts like a center conductor of the coaxial line. This is the in between space between the inner conductor and outer conductor, and this together makes the outer conductor. So, the CPW line is called a planar version of the coaxial line. Say for example, if you take a coaxial line and cut it right through, you will get this type of this thing. And just like in the coaxial line, the electric field is like this. So, here since this is at a higher potential, this is at a lower potential, the electric field line will be like this. and the field distribution over here and here are likely to radiate, but because the electric field here in this case is in this direction, here it is in this direction, they are oppositely directed. So, the net radiation is 0. So, that is why in the CPW lines, CPW feed, although it is a planar in nature, but the spurious radiation is less. Okay. We go to the next aspect, the polarization purity. In the case of coaxial feed, there is a problem with the polarization purity. Yeah, there are going to be field lines here also where it is feeding, and from here there is going to be extra radiation, and that compromises the polarization purity. Whereas the patch antenna is supposed to give polarization like this, okay, but this is going to give this type of polarization, and that is how the polarization purity gets compromised over here. It is a poor polarization purity is poor, but this one radiating edge coupled, there is no problem as such, whereas again the polarization here, all of these cases it gets compromised, but not in the aperture coupled type. Okay. Whereas in the case of CPW feed, again the polarization purity is maintained in the sense there is hardly any radiation from the feed. So, whatever be the polarization if your antenna, that remains as such. So, the polarization purity is a problem because of the feed radiation. Wherever you see that there is a more of feed radiation, polarization purity is poor. It is less, so polarization purity is better. Here it is less, polarization purity is better. But this is an altogether different case. Although spurious radiation is more, but it does not add to the polarization problem because the ground plane separates the two parts. Ease of fabrication, you can see that wherever you are using the printed lines, it can be fabricated along with the rest of the circuitry. So, it is easy to fabricate the feed line along with the other, except for the case of this coaxial probe, where you require soldering and drilling, because you have to drill through the substrate so that the center conductor can pass through it, and the center conductor, other end of the center conductor has to be attached to the metallization, and not only it should be attached like this, you have to solder it over there. So, for some of the applications, for let us say aerospace applications etc., where there is a lot of mechanical vibration, they try to avoid this coaxial feed, because due to mechanical vibration the soldering may come out. Okay. Then reliability, naturally when you are fabricating everything, all the circuitry etc., in one go using the printed circuit technology, the reliability is going to be better. Whereas in this case the coaxial probe, the reliability is going to be poor, that is what is written over there, otherwise it is better and good. Impedance matching, radiating edge coupled feed, the impedance matching is a problem because the input impedance at the radiating edge is very high. Okay, either you introduce an impedance transformer or you can introduce a gap. Okay. Bandwidth, we can see that more or less the bandwidth is between 2 to 5%, not much. And I think in all these cases it has been assumed that the substrate dielectric constant is around 2 and the substrate thickness around 1/16 inch. So, if you increase the substrate thickness, your bandwidth will increase, but the conformal nature will get compromised. You may not be able to make it conformal if you use a thicker substrate. Now, typical characteristics. Okay, this was the preliminary part. Now, we are looking into the what are the radiation characteristics of the antenna in terms of its bandwidth, radiation pattern, and the radiation efficiency etc. Okay. First of all, because it has a resonant behavior, its impedance characteristics will be of this type, that the real part of the input impedance with frequency is going to be like this, and the imaginary part of the input impedance is going to be like this. And at resonance you can see the resistive part is maximum and the reactive part is 0. That is what characterizes for any resonance characteristics, the reactance or susceptance has to be 0. Okay. And the equivalent circuit now for a patch with this type of electric field distribution over here between the patch and ground plane, the current on the patch metallization will be like this, and these are the fringing fields shown over here which accounts for the radiation. So, the equivalent circuit for this one can be put in terms of a parallel combination of L, equivalent L, C and G. This G accounts for the power radiated. So, if one can find out the equivalent L, C and G, one can calculate what is the input impedance. Okay. So, it is a parallel resonant circuit. These are the typical characteristics. You can see over here that this is a rectangular patch with some particular dimension where the substrate thickness is 1.59 millimeter, means 1/16 inch. Epsilon r substrate dielectric constant is 2.62 and tan delta of the substrate is 0.001. Okay. It has been designed, I think something around 1100 megahertz, and this is okay, where it is fed, it is being fed over along this dimension. We are feeding along this dimension. So, this is the dimension which is determining the resonant frequency, 7.62 centimeter determines the resonant frequency, and there are 3 feed points 1, 1, 2 and 3. The 1 which is almost at the center, this is the impedance locus, that as you vary the frequency the impedance is going to vary. This is Smith chart, and you can see that the real part of the impedance is quite high, okay. And it is a small locus, right, because it is in the center. If you shift it towards the edge, then the impedance locus changes like this, and it passes through center of the Smith chart where the impedance is 50 ohm, passes through the unit circle over here. Whereas, for the feed point number 3, the impedance locus, this is the impedance locus. Okay. So, you can see looking at this one, this is the for only for this feed point, at some frequency it passes through the 50 ohm point. So, that is the most suitable. As you go away from this one, either the impedance locus becomes smaller or it becomes larger. Okay. And in all the cases, whether you are designing a rectangular patch, circular patch, the variation of the impedance with respect to frequency is going to have this type of impedance locus. Okay. Okay. Now, this is about the radiation pattern measurement. How many of you are familiar with how to carry out the measure the radiation pattern, or how many of you have done the radiation pattern measurement? Huh? No, other than the spectrum analyzer or whatever receiver you use, how do you position your receive antenna, and from there how do you determine the polarization of the received signal? Because when you are measuring the radiation pattern, normally you measure the radiation pattern in 2 orthogonal planes. That is, if you, this is your patch antenna, you will measure the radiation pattern in this plane and this plane, 2 orthogonal planes, going from one end to this one like this, going this to this half sphere. Okay. Along the half sphere, you move your receive antenna Say if this is, let us say, the patch antenna. Okay. So, in one case the receive antenna will move like this, in orthogonal plane it will move like this. Okay. And receive antenna, normally if you are using, let us say, the horn antenna can be rotated, and that will determine the polarization. Say for example, you have one particular orientation of the horn antenna, it will go like this, then you rotate it through 90 degree, again take the radiation pattern, you will get a different component of polarization. Similarly, in this plane also. So, normally you have to take 4 measurements while measuring the radiation pattern. E theta, one is called E theta polarization, other is called E phi polarization in this plane as well as in perpendicular plane. These 4 measurements have to be done. Now, this is what is shown over here. Let us say this is x axis, y axis and z axis, and you are going from, let us say, z axis is top, this one is z axis. You start the horn antenna going from here to here or going from here to here, and if your aperture of the horn antenna is like this, okay, like it is shown, then you are sensing this component of the electric field, and this component of the electric field, since it coincides with this, so you are sensing the theta component of the radiated field. So, if your horn antenna is polarized like this, receive horn antenna, you are sensing the E theta component, and if you turn this antenna through 90 degree, receive antenna, turn it through 90 degree, then you will be measuring the E phi component of polarization. Similarly, let us say if you go from this plane to this plane, okay, then if your horn antenna is polarized like this, then you are sensing the phi component, because this is how you define the phi. Otherwise, if you turn it through 90 degree, you will be measuring the theta component of the electric. See, understanding this thing is not so easy. That is what I put it over there. Most of the students get confused. What is E theta? What is E phi? Whether they are measuring E theta, whether they are measuring E phi, and it is the this aperture of the horn antenna and how you are moving it that decides it. Okay. Yeah, these are the typical radiation patterns. This is E theta plot in phi 0 plane. This is the rectangular patch we have shown over here, and if your horn antenna is like this and you are moving from this to this, then you are sensing the E theta component, okay, in the half space. And this is how the radiation pattern looks like, that at theta is equal to 0, that is right in this direction, perpendicular to the patch, you are getting the maximum 0 dB. As you go to 90 degree, you can see that the corresponding it is reduced over, this is 0 dB over here, at theta is equal to 90 degree, it has become something like this is 10 dB, this is okay, this is 0. So, this is something like 5 dB down, 5 dB down over here for the case which is epsilon r 2.32. So, here it shows the effect of the substrate parameter on the radiation pattern. For epsilon r 9.8, which is a large one, you do not see that there is any change in radiated field with respect to theta. Here also it is 0 dB, here it is also 0, almost 0 dB. That means, if you are using high dielectric constant substrate, there is hardly any radiation. But for epsilon r 2.32, the inner one, here it is 0 dB, at theta is equal to 90 degree, it is almost 5 dB down. Okay. This is about the E theta component in phi 0 plane. Phi is equal to 0 degree plane. If we go back, this is phi is equal to xz plane is equal to phi is equal to 0 degree plane. So, if you are taking the measurement in the xz plane and measuring the theta component, then you will get the, you should expect radiation pattern like this. And in phi is equal to 90-degree plane, that is YZ plane. Phi is equal to 90-degree plane is YZ plane, and the E phi component plot will come out like this, that at 0 degree it is 0 dB, at 90 degree it is almost no radiation. Okay. The reason is that E phi component becomes tangential to your ground plane at at theta is equal to 90 degree, and since E phi component is tangential to the ground plane, so the corresponding component has to be 0 because of the boundary condition over there. So, here it becomes 0 over there, and this is what is shown over. Phi is equal to 90-degree plane is this one, so far as your antenna is concerned, and your this receive horn should be polarized like this. Directive gain of this antenna is 5 to 6 dB, as you that is what you should expect, because it is a dipole antenna, and the gain of a dipole antenna is about 6 dB. Okay. And the beam width is from 70 to 90 degree. Okay. These are the typical radiation characteristic of the patch. This is an interesting one, that is variation of PR is the radiated power, PC is the power loss in the conductor, and PD is the power loss in the dielectric. That is, whatever power you are feeding to your antenna, whole of it is not getting radiated. Part of it is getting radiated, which we call it as PR. Part of it is getting lost in the conductor, because the conductor which we are using is not a perfect conductor. It has a finite conductivity, not infinite conductivity. And the dielectric which you are using, that is also a little bit lossy. So, part of it will go in heating the dielectric, and the less the value of PC and PD, more is going to be PR. Now, it shows how to increase PR with respect to PC and PD. Naturally, it will depend upon the substrate parameters and the metallization, etc. Okay. So, here two cases are taken care of, epsilon r 2.32 and epsilon r 9.8. So, what we should expect is that when epsilon r is equal to lower value of epsilon r, you should have more of radiated power, PR should be more percentage wise, whereas for epsilon r 9.8 PR should be less. Okay. Let us concentrate on this one. This is PR over PT. Okay. That is radiation efficiency. Let us compare these two cases. One is epsilon r 2.232, one is epsilon r 9.8. You can see clearly the radiation efficiency for the lower dielectric constant is more than the higher dielectric constant. Similarly, PC power loss, here it is more, where in the low dielectric constant is less, and PD, yeah, this PD is naturally very small, you can see in both these cases. So, most of the time when you are using a substrate which is a low loss substrate, and in fact these are the specialized type of substrates which we use for the microstrip antennas, and they are damn costly. Okay. Something like which we have said about something like 10 delta 0.001. This is a highly costly substrate, and as a result the corresponding loss in the substrate is less. That is why it is shown that compared to the power loss due to the conductor and radiation, this loss is very small, and most of the time we can neglect it. But these days, so far as doing the experiment for your own research or studies, there is a substrate available which is quite useful and easily available. I think that one is FR4 we call it. I think this is Teflon fiberglass or which one? Teflon fiberglass substrate is available, which is like a normal PCB. Its dielectric constant is around 4, and loss tangent is around 0.02. It is quite cheap, easily available, and most of the studies these days, even for research application in the educational institute, we use that type of substrate. It is a good compromise so far as the dielectric constant is concerned, neither it is too low, dielectric constant is neither too low nor too high. Maybe the low dielectric constant, if one can afford, is 1, is good enough, for which one uses the honeycomb structure, which the dielectric constant is almost 1, but 9 or 10 is does not give rise to radiation. So, it is a good compromise between 1 and 10, and it is quite cheap also. Okay, this, if we calculate the quality factor just like any resonator, that gives you all the information from the circuit point of view, that will tell you about the bandwidth, etc. Okay. And we know that the quality factor, just like any resonator, we define as the ratio between the energy stored and the power loss per cycle. And energy stored, the electric energy half epsilon E square, okay. And epsilon basically over here, electric field is going to remain the same for a given amount of power fed to it, and epsilon is going to determine the energy stored. So, higher the value of epsilon, other parameters remaining the same. So, the energy stored will increase and naturally the Q will increase. Okay. Similarly, the power loss is found to be inversely proportional to the dielectric constant. So, if you combine the two, you will find that the quality factor of the antenna is directly proportional to the dielectric constant square. Okay. That is, larger the dielectric constant, larger the Q of the antenna. Although we are talking about it is a resonator, the antenna we are using, it is a resonator, but not a perfect resonator, it is a lossy resonator, because it radiates power. So, it is a lossy resonator, and the Q of this lossy resonator is proportional to the dielectric constant. So, if you increase the dielectric constant by a factor of 2, Q will increase by a factor of 4, and when Q is more, what happens to the bandwidth? Bandwidth is going to decrease, because how do you define Q? Yeah. Okay. Or okay. So, if you increase the Q by a factor of 4, your bandwidth will go down. You can call it delta F. That brings out everything from the circuit point of view, that how the substrate parameters are going to affect the Q and the bandwidth. Say, if you right now we are talking about the dielectric constant, but you can look at it from the substrate thickness point of view. If you increase the substrate thickness by a factor of 2, what happened to the energy storage? What happened to the capacitance? Okay, we can put it that way. If you increase the substrate thickness by a factor of 2, what happens to the parallel plate capacitance? Capacitance will decrease, and energy stored will decrease. So, Q should decrease, bandwidth will increase. That okay? That is what these plots are. You can fit into that type of physical reasoning, that how variation of Q and bandwidth, how the Q and bandwidth vary with the resonant frequency. And you can see this is a total Q and this is the bandwidth. And you can see that here bandwidth for epsilon r 2.32 is more, and as the substrate thickness increases, this is the substrate thickness 0.318 centimeter, bandwidth is more, 0.159 this is the bandwidth, which will be something like half of that, and if you reduce the substrate thickness, bandwidth decreases further. Okay. And same thing you can see in the case of Q. For epsilon r 2.32, the Q values are lower between 10 to 100, whereas for high dielectric constant, the Q is total Q is more than 100. Typically, for a patch antenna, the Q will be something like 50. If you use epsilon r 2.2 and 1/16 inch thickness, it will be around 50. Okay. That is, the bandwidth is inversely proportional to 1 over Q. These are the gain, directivity, and the radiation efficiency. Now, let us look at the radiation efficiency first over here. You can see that for lower dielectric constant, it is almost touching 100% for a thicker substrate. When the substrate thickness decreases, the radiation efficiency will also decrease. The directivity, this one low dielectric constant will have a larger directivity, which is around 6 dB, whereas high dielectric constant will have a low directivity between 3 to 4 dB, and gain is near 5 dB over here, again is near 2 dB gain. So, all these things explains that why we use low dielectric constant substrate and larger thickness to improve the performance of the antenna. And this tells you the selection of the substrate in one nutshell, that here it is a substrate thickness h by lambda 0. You can see that for epsilon r 2.2, I think this is the bandwidth. Bandwidth is almost linearly increasing with the substrate thickness, going up to 15% bandwidth when h by lambda 0 around 1 by 10. When thickness is lambda by 10, it makes something like 15%. And efficiency is between 80 to 100% for epsilon r 2.2, depending upon the thickness, and here the efficiency comes down drastically from 100% to almost 40% with epsilon r is equal to 10. The reason why the efficiency decreases with the increase in the substrate thickness, see, we have seen that the efficiency, the bandwidth increases with the substrate thickness, but the efficiency decreases, radiation efficiency decreases. The reason are that in these antennas there is a substrate and some of the power goes into the substrate modes. Whatever power you feed to the antenna, most of it gets radiated, but some of it goes into the substrate modes, and that is a loss of power and decreases the efficiency, and the power in the substrate modes increases with the increase in the substrate thickness, unless if we are using epsilon r is equal to 1. If we use a substrate which is close to 1, then there will be any power in the substrate modes, and radiation going efficiency is going to be almost 100% independent of the substrate thickness. PC depends upon the power loss in the conductor, depends upon the your conductivity of the metallization. PD depends upon your loss tangent of the substrate, especially if you are using let us say honeycomb structure for the substrate, where the dielectric constant is almost unity. I think in most of the cases for honeycomb structure, the dielectric constant is around 1.1, but it provides a very good mechanical support also. So, radiation efficiency is almost 100%, and power loss through the substrate modes is almost 0. And because the substrate also in the honeycomb structure, the amount of substrate is very small. So, the dielectric loss is also less in that case, but these honeycomb structures are damn expensive. Okay? It is a trade-off. Okay? What is the basic of the planar antennas we have covered today. and rest is about the what are the methods of analysis, which includes the simple models like transmission line model, cavity model, and then there are this thing numerical techniques are there. And I think after that the cavity model and limitations, the full wave analysis. This is FDTD. Maybe let me show you one thing over here. This is about the this is just like I am not giving you any background, just telling you the power of one numerical technique. This is a rectangular patch antenna which is being fed by a microstrip line. The parameters are adjusted so that the at here the input impedance is I think 50 ohm, and this is the return loss plot of this one. Maybe this is the resonant frequency where the S11 return loss is around 15 dB. And one interesting thing over here, this antenna has been analyzed using finite difference time domain technique. The finite difference time domain is a numerical technique, and it produces animation of how the field varies at a particular point in the antenna as a function of time. So, for example, these are the snapshots of the field distribution taken at different time steps, 200 time step, 400 time step, 600, 500, 800 and 1000 time step. And the one time step will be something like a certain picosecond. Okay. So, it shows that from here there is a, this is a feed line over here, there is a patch at 200th time step, the whatever the signal you are feeding, it has traveled up to this point, nothing on the patch portion. As the time progresses, this signal now reaches this is the patch portion, and that is how the electric field distribution here, somewhere it is maximum, somewhere it is less. And now at 500 600 time step, now after getting reflected from here, it is trying to come back, that it is trying to simulate as the wave progresses with time, some places there are some reflections, and due to this reflection the overall field distribution is going to change. And then at 800 time step, you can see that whole of it is filled up now, the feed line as well as the patch. And 1000 time step, you can say that the resonance mode is got set up and it is trying to move away from this side.
How could we divide the time in picoseconds practically?
No, it is simulation. But if you are talking about practical now, talking about the picosecond, now there are signal generators available, pulse generators are available. I think which you can buy of the order of with rise time less than 1 nanosecond. Okay. And these are damn expensive, especially if you want to you normally use it if you want to carry out time domain studies of some circuits or antennas whose bandwidth is quite large. So, you have to generate the pulses whose width is less than a nanosecond, naturally the rise time should be less. That is okay. I think we can stop.